Okay, so this is the Sturm-Liouville eigenvalue problem. I'm going to leave this part up here and erase this. But basically, we're going to be assuming that we're doing a regular Sturm-Liouville eigenvalue problem, which means that P, Q, and sigma are all real and continuous, and we're assuming that, P and sigma are positive. And why we're assuming those positive and Q isn't is going to make sense when I start, mentioning where we've seen these things before. Okay, so this should be a short video. So, when P is equal to sigma, and they're both equal to 1, so just the constant function is equal to 1, and Q is equal to 0, this Sturm-Liouville equation just becomes phi double prime is equal to minus lambda phi, or phi double prime plus lambda phi is equal to 0, with boundary conditions. And of course, we've seen this differential equation before, but maybe not as general boundary conditions as we normally get. Okay, so for the heat equation, so this is just something we've seen before. For the heat equation, or the diffusion equation, specifically for the heat equation, P is equal to K naught, which is the diffusion coefficient. And remember that when we derived the heat equation, that was assumed to be a positive quantity. Q, for the sort of heat equation that had a source that's proportional to the temperature, we would have something like, I lost my spot on my notes here. We would have something like Q is equal to little q times U, and then sigma would be equal to C times rho, where again C is the specific heat coefficient and rho is the density. So here, remember K naught is positive. Here, both the specific heat and the density are positive, so therefore sigma is positive. But here, this little q could be positive, q could be positive or negative, so therefore little q can be positive or negative as well. If we looked at the string equation, so let me write down the string equation for a non-homogeneous string was rho times the second t derivative of U is equal to x times t, which is the tension in the string, times the x derivative of U. And then if we have some sort of external force, rho alpha U, so like this would be maybe like the force of gravity or something, this is going to depend on U itself. And so the corresponding Sturm-Liouville problem would be the derivative with respect to x of t times the derivative of phi with respect to x plus rho alpha phi is equal to minus lambda rho phi. Okay, so here p would be equal to t, rho times alpha would be equal to q, and then rho would be equal to sigma. And those all satisfy the positivity and the regularity conditions that they need to satisfy. Okay, so that's it for this video. Again, my point in doing this video is just to say, yes, these are things that we have seen before. The Sturm-Liouville eigenvalue problems are things that we have seen before. At least they're motivated by things we've seen before, I guess is how I should put that. And so now the idea is there a general framework in which we can work to take all of these different problems that all kind of have the same, like all of the x stuff, all of the, we have the time stuff and the space stuff, all of the space stuff kind of works together, or there's sort of a general framework for all of this space stuff, no matter what the problem is. And we kind of want to work through that and see exactly how general we can make it, what the connections are between these branches or between these different equations, and stuff like that, because oftentimes knowing what's going on in the space variable alone is going to tell us a lot about the problem in general. But that's it for this video. I'm going to give you, for the next several videos, I'm going to give you some very general properties that all of these Sturm-Liouville problems satisfy.